Hi, this is Keenan Casey for TutsPlus.com. In this lesson, we're going to be looking at Ethernet, which is standardized in 802.3. Ethernet is a simple, connectionless, unreliable link layer protocol that happens to be the dominant wired local area network technology. It has a long history and it's evolved a lot over the years. In this lecture, we're going to look at the format of Ethernet packets, talk a little bit about MAC addresses, and talk about CSMA CDs, some letters that mean a lot to the design of Ethernet. You can see on the right here actually the original sketch for Ethernet by Bob Metcalfe, the man who invented Ethernet. And as you may be able to see, that yellow line is the ether. That is, it's the wire that's shared by all of the computers and that carries the communication between all of them. It's a shared communication mechanism. This was the original design for Ethernet, and it's evolved a lot since then. Two important properties of Ethernet are the fact that it's connectionless and the fact that it's unreliable. It's connectionless, and that means there's no idea of a connection that's set up ahead of time. There's no handshaking. When a computer wants to send, it sends. It blasts away without forming a connection to the receiver. In fact, all the receivers then are constantly listening to see if there's something about to be sent to them. Secondly, Ethernet is unreliable. It doesn't have acknowledgments or negative acknowledgments. If packets aren't received correctly, they won't be resent due to Ethernet. Now, we know that there may often be a reliable data transfer protocol running at the transport layer, like TCP, that will cause that data to be resent. But Ethernet doesn't provide that reliability. This is what an Ethernet frame looks like. You can see that there are 5 different pieces of an Ethernet frame. To begin with, there's a 7-byte preamble, and this is a set pattern of ones and zeros that helps the sender and receiver synchronize with each other. It's a flag that the receiver is looking for. Next, there are 2 6-byte addresses. These are MAC addresses, the first being the destination's address, the second one being the source address, the sender. Next, there is a 2-byte type field. The type field indicates which higher layer protocol is encapsulated in this frame. Typically, that's going to be IP, the Internet Protocol, but there could be other protocols as well. The payload is in the data field. You can see it can range from 46 to 1500 bytes. And lastly, there's a CRC, a cyclic redundancy check, which implements the error detection by Ethernet. This is checked at the receiver, and if an error is detected, then the frame will be dropped. The packets become corrupted. You can see that then this is the final size of an Ethernet packet. Next, let's talk about IP addresses and Ethernet addresses. You may remember that an IP address in IPv4 is a 32-bit number that is specific to the network layer. An IP address represents a number that's been assigned in a hierarchical space. That means that you have to have the right IP address for the network that you're located in. A result of that is the fourth thing on this table: IP addresses are not portable. If you go to a different network, you're almost certainly going to have to get a new IP address. On the other hand, MAC addresses exist in a flat space. There's no hierarchy. All the numbers, all the addresses in the MAC space are basically the same. Because of that, MAC addresses are portable. Your MAC address does not change if you go to a different location. So this is sort of a summary of the differences between an IP address and a MAC address. Your computer will have both. A human analogy might be a MAC address is like a social security number. That's always the same number, a very unique address. Whereas an IP address is more like a postal address. It is going to depend on space, and it does represent a hierarchy. This diagram illustrates how the original version of Ethernet worked. Essentially, the wire connecting all these computers was a shared medium. This represents a bus topology, and only one person could be talking on the bus at once. The original speeds were of about 10 megabits per second. And this was done over coax cables. What we see is the original Ethernet was a shared broadcast medium. Now that has changed over time, but let's talk a little bit about some of the nuances of a shared broadcast medium. What happens if two computers transfer packets at the same time? That will cause a collision. The two packets will garble each other and neither one will be understandable by their receivers. So a collision is bad. We'd like to avoid that. Why are collisions bad? Because they lead to wasted time and wasted bandwidth. To solve this problem of collisions, Ethernet presents an algorithm called carrier sense multiple access. And the idea behind this is very simple. Basically, every computer on the network will listen before it starts transmission. It'll listen before it talks. If no one else is talking, then the computer will transmit. If it hears someone else talking, then it will wait. It'll defer transmission. A human analogy on this is basically don't interrupt others. If you're having a conversation, don't start talking if somebody else is talking. That would certainly be impolite. Now the next question is, can collisions still occur if we always listen before we start transmission? And the answer is yes, whether you're a human or a computer. If two computers start talking at the same time, or at least before they hear each other, then their transmissions will collide with each other. So how can we solve that problem? Well, the next step is CSMA with collision detection. Basically, this means that we listen while we're transmitting. And if a station hears anything besides its own transmission, then it knows that there's another colliding transmission that's going on. In this case, the human analogy is like a polite conversationalist. It's a person who will listen while they're talking, and if someone else starts talking, they'll both pause and defer to one another and try to decide who gets the stage, who gets to keep talking. In wired LANs, it's easy to do this collision detection because we can measure the received signal strength and compare it to the transmitted signal strength, and that it ought to be the same. If not, then we're probably colliding with somebody. In a wireless environment, however, it's very difficult to do collision detection because it's hard to listen to other signals while you're transmitting. And we'll talk more about this in the Wi-Fi lecture. Let's talk about how Ethernet implements the carrier sense multiple access with collision detection algorithm. First, a frame will be created. It'll then check the channel and see if it's idle. If the channel is not idle, we will wait and check again. Well, what happens when the channel is idle? We'll go forward and transmit the packet. After and during the transmission, we'll check to see if there's a collision. If there is a collision, then we're going to go into a phase called backoff. Backoff essentially waits a random amount of time and then tries to retransmit. So after we go through this backoff algorithm, we'll choose this value k, which we'll talk about in just a second, wait k times the amount of time it takes to send one bit, and then try to retransmit. We will do this until there aren't any collisions, at which point we will be done sending. Let's explain this exponential backoff phase a little bit better. Backoff uses two variables, m, which represents the number of collisions, and k, which is going to be the wait time. The algorithm keeps up with how many collisions have occurred. After one collision, the wait time will be between 0 and 1. After two wait times, that'll be a number between 0 and 3. After 10, it'll be a number between 0 and 1023. So you can see that the wait time may expand exponentially as more and more collisions happen. The question we might ask is why? Why do we go through this backoff process? And the answer is that this algorithm will adapt the retransmission delay to the current load without ever even knowing what the current load is explicitly. A modern Ethernet looks quite a bit different than that original Ethernet. Modern Ethernets involve switches. Switchers are a very intelligent link layer device that learns which devices, which computers, are on what links, and it only forwards frames to the appropriate links instead of sending it to everyone. Another way of saying this is switches selectively forward packets using a self-learning algorithm. A modern Ethernet has a star topology where each host has a direct connection to the switch. Furthermore, each link is full duplex. That means it can send and receive at the same time, and it's in a separate collision domain. So for example, each of these links was a different color because it's its own collision domain. Each link is the only area that collisions can happen. So what that means is modern Ethernet is switched and it's a collision-free environment. Speeds currently run up to 1 to 10 gigabits per second on modern Ethernet. As we conclude, let's think about this question. Why is Ethernet the dominant link layer protocol? And I've got about 3 answers to this. Number 1, Ethernet is simple, and simple is good. Simple almost always translates into cheap to implement. Secondly, Ethernet has always been fast enough. Been competitors, but Ethernet has always remained fast enough to be competitive, and it just keeps getting faster. Thirdly, Ethernet is cheap. It's always been quite inexpensive relative to other technologies, and everybody likes cheap. As we've also said, Ethernet's adaptation has supported its progress in increasing speeds and its continued success. Ethernet has never been afraid of changing, and you can see that modern Ethernet is very different than the original version of Ethernet. This has been a quick look at Ethernet, the dominant wired link layer protocol. I'm Keenan Casey for TouchPlus.com. Thank you for watching.